I'm going to get started. Hopefully, fingers crossed, your Wi-Fi is working well enough to connect to the server. If not, this will still be available for you. It's still in the curriculum. Like I'm going to follow it as a template, but of course, as like that yesterday, we're just going to sort of trudge on through together. All right, so where we last left off, we had a notebook open, so I'm going to start a new one. Just as a reminder, in case you did restart your server, we do need that extra library. I'm going to show you again how to download and install with Python pip in order to get the package to get the bold data. So remember, it is in a cell. If we start off with an exclamation point, it's telling the interpreter that this is a line of bash script, essentially. Python -m pip install and nds lib. And if we run it, I think I did install this morning, but who knows? It'll give us a bunch of output telling us that we're doing some installment. Yes, of course. No, you're good. Let me make it a bit bigger too. Python -m pip install nds lib. Are you in a Jupyter notebook? No, would you mind? Sorry.
Do you have an error for the last line?
If we scroll all the way down, scroll.
Yeah.
It says error dependence. There's like sometimes, depending on the package that installs, it's more, I would take it more as a warning than an error. If it's still sort of successfully installed.
Okay.
And if anything, I think the function that we're using doesn't depend on any of the things that it's telling us it depends on. So I'm not too concerned. I'm just going to comment it out so that we still have that line in that cell in case someone still needs it. And add a cell at the bottom and actually import the libraries that we'll be using for the rest of this particular notebook. Talking about NumPy as NP from NDS lib imports load data. So importing the NumPy library as NP for shorthand, import from this package that we just installed or library that we just installed, import the function load data, just to make sure that we can get our bold data. Give that a run, give it a second. And everything is successful. One, there's no errors in your output, but also there's sort of a number that says you've successfully made the cell run. All right, loading the data again. Bold equals load data, calling on that function. If there's no output?
No.
Like if there's nothing, what?
Yeah, so if I run it and I got nothing, doesn't mean it's.
Yeah, there's no error message, like there's no giant red. Does it look like my output?
Oh, okay.
Yeah. Okay. So we're loading in the data set bold underscore NumPy, fname equals bold dots npy. And you'll sort of see actually from yesterday, 21 hours ago, almost, wow. I downloaded it the previous time, so it was still in my working directory. But just in case you guys don't have it, I just wanted to make sure that you all had it. Give this line a run or give this cell a run. And nothing, if there's no giant error text, and if there is a number here in the square brackets indicating that it has run successfully or completed running successfully, we should have our bold variable with our bold data. And so we can inspect it. Actually, new cell for me, bold.shape, just to print it out. Reminder that this is a 4-dimensional NumPy array where we have X, Y, Z, and then time. And just to show you, this is not the visualization lecture, but I am going to just start doing some things just to show you what the data actually looks like in here, or what it would look like in here. I'm going to import another package, matplotlib.py plots as PLT. This is also pretty standard convention. The package name itself is matplotlib. And if you can sort of guess where its inspiration comes from, it's from a bunch of MATLAB functions. PyPlot is the one subroutines. So like basically a section or subcommands specifically in the matplotlib package that we'll be using on, and plot just short for plot for shorthand. It's already on the server, so that one should import with no issue. And then plot, call the plotting commands. IAmShow. Again, if you guys are familiar with MATLAB, this is sort of very familiar. Our data is in 4 dimensions, but IM show is image show. It's trying to expect just a 2D matrix. So let's just pick 2 dimensions to sample down and then just plot it as an image. I'm just going to go to bold subsets colon for all of the first dimension, colon all of the second dimension, and pick some 2 random numbers, 12, 0, just because I can. If I try to run this, ta-da, we get a little break. We also get this fun matplotlib image, axis image. This is pretty much the output of this line. Sometimes I like to suppress it by just doing plot.show, just to suppress additional text. It doesn't have to be, the image will still plot if you plot it. But here we are. Here is a transverse or actual slice through, I think, roughly around here-ish, of the first time point we have for this bold data spatially, right? And then I could obviously change these numbers up. Let's say I have 64 of them, so let's say 32-ish, 32-ish. Oh, I should probably still do 2 dimensions spatially. Right. There we go. There's our sagittal view, and the other one is going to be our coronal view. But I like to. Okay. Every second. Fingers crossed. Thank you. Yes.
I'm sorry, is that in map show or is it end in show? Sorry, I can't.
Oh. I'll make it bigger. I am sure. I am sure. Okay, maybe not that big. I can't read. I can actually probably press some of these. Okay. Just as sort of a visualization scheme, just take a look at our data. All right, so the other way besides spatially to look at bold data, if you have it, is we can also look at it across time. And so we can sort of extract out a time course, and I'm going to call a variable called time course. And from our bold data, I'm going to just pull out somewhere in the middle. Like I'm going to pick a voxel, one particular pixel, somewhere in the middle-ish. All the time points, which is our last dimension. And we can double check that I will be getting the right dimensions by checking the shape of it once I have it extracted. And cool. Time course, the variable has a shape of 180. I know there's 180 time points or number of volumes in this particular bold data sets. And so this is good for me. Another way to really quickly take a look at it is plot.plot. Also spell plot with a 0, with an O this time. Time course, and just to suppress that output message. Cool. And we have our time course data. If you know the particular quirks of bold data, the y-axis values are arbitrary. These are just randomly scaled. That's sort of how it comes off the scanner. And I'm assuming, and I'm also extrapolating that such that if you do EEG, intracranial work kind of stuff, you'll also be able to plot these time series in whatever dimensions you particularly need to slice them in, number of channels, number of electrodes, so on and so forth. But for bold, this is just sort of how they look. They look like wiggles because they are wiggles. All right. So I kept on exposing a little bit about why NumPy is really good for mathematical operations, especially on time series kind of data. And that's because in base Python, we can't do math on these arrays really naturally, like element wise or vector wise or matrix wise. So just to demonstrate a really simple operation that we oftentimes do on bold time series, let's just normalize this time series. So putting a cell on the bottom, making a, spell correctly, normalized time course. And we can do pretty basic math. Subtract, take the actual time course, subtract it by its mean. Time course, and this part is probably where NumPy comes in clutch, is that we also have a dot mean operator on this NumPy array vector. Basically, take the vector, grab the mean. You can do it along any of the axes. There's an additional specification where you can specify which axis or which dimension you want to take the average on. Considering that this is a one-dimensional vector, this will be the only dimension it takes the mean on. Mean, keep my parentheses close, divided by time course dot SC, divided by the standard deviation. So really quickly run that on my time course, looks good. Plot, stop plot, just to make sure. And let's do that in the next cell. And you'll see it looks exactly the same, but the y-axis have been scaled, and that's good. We did what we wanted to do. These two time courses look exactly the same. I'm going to stop right here because that was a lot of typing, in case you wanted to grab that. So basically what's buried in here in the NumPy arrays is a bunch of functions, sort of like those string functions I showed you yesterday, sort of like all those other kinds of additional methods that are buried into these types. We can examine them with that dir function shown yesterday. So normalized time course, that variable. What's in here? We have a bunch of other stuff, right? And I was just referring to, if I can find it, long list, mean, right? There is that mean method in there, as well as the STD for standard deviation. We also have round, we have reshape, right? A lot of these operations that you want to manipulate your arrays into different ways, do math along them in different axes, they're readily available for you in these NumPy arrays because they are NumPy arrays. I'm gonna again suppress this one because this is really long. We'll cut it out. All right. Before I move on, any questions? Yes.
Go back up.
Yep, going back up. I thought from the owl.
On the like where you have panels that you in like feedback, like what an example of what you use that in that?
Oh, in the brackets?
Yeah.
So let me really quickly go down. Well, hold on one second. The person on the owl who spoke up, is it okay to move on?
Yes.
So let me give you like a 2D image real quick. Image, nope, IMG, bold. Gonna grab something at random, okay? I hope that's right. Great. So this is a 2D matrix, just grabbed randomly. Do the mean. If I just call the mean on it, it's the mean of every single value in there. Right? If I flatten that entire 2D matrix, just grab the mean, that's the number. You can also do axis equals 0. And now we have a lot of numbers. Check the shape on that. 180. Oh, I did the mean along the first dimension. So for, oops, my bad. Let me print this out one more time. Print the shape, right? We have the first dimension, 25 row-wise values, 180 values column-wise. If I do the mean along axis 0, I'm basically row-wise sum, taking the average row-wise, right? Second one, if I do axis equals 1, I should get 25 values, and I do. There's additional arguments in there, and they're buried into documentation as well. Like if I remember correctly, I think there's something called keep dims equals true, and it just gives you an actual singleton dimension at the end of this array as an output, just to give you some shape so it matches up with other things you want to do math with. So all these methods themselves, you can think of them as built-in functions associated with this object that this NumPy object I keep on referring to. They themselves have arguments, or they don't have arguments. You can read up on the documentation to see the specific ones. Okay, well, alrighty. So let's do something of a little bit more complicated, where, okay, it's really nice to be able to do a normalized time course one at a time, but that would sort of defeat the purpose of having this giant matrix all shaped nicely for us. Let's try to normalize the entire gold series. And one of the nice ways we can do it is just playing around with some of those built-in functionality that I mentioned. First, let's extract some of the values that we care about. So how many voxels are actually in this bold data? Well, checking the shape, move this up a bit as well. We have 64 times 64 times 25. That's however many number of voxels or pixels we have in this cube. And so let's make that a variable. N voxels equals, and then you can use NP prod, which is short for products, and take the 0 through third position because it's exclusive. And that'll give us the product of 64 times 64 times 25. I can check that. I cannot check that if I spell things wrong. Okay. I can double check that by doing it manually. I can't do that many multiplications in my head. Okay, we're good. All right, that's the number of voxels we have. Cool. Let me be very explicit. Pull out the number of time points we have. Bold dot shape referring to the last value. I could either put in 4, refer to the last value in that shape array, or I can do -1 to refer to 1 from the end. Sort of up to you how you'd like to do that. Time points, double check, 180. Cool. We're good to go.
What were the 2 options that you mentioned?
And in this case, because the vector size is length of 4, I can also go bold dot shape in parentheses. 4. Okay, I'm just gonna save it as untitled. Oh, 3, sorry. I cannot math this morning. Alrighty. So we can now reshape the bold data such that instead of having it be 4 dimensions, let's actually flatten one dimension, flatten it to 2 dimensions, where all the voxels themselves are a row column and every single time point is a column. Pull the last index, pull the index from 1 from the end,
Okay.
from the back. All right, so bold reshaped as my variable, take the bold, and we passed by when I did that dir call, a reshape functionality for these ND arrays. I'm going to reshape it to n voxels, still voxels, n time points, and then check the shape. Bold reshaped, reshaped, dot shape. Give it a second. Cool. And now the shape of bold reshaped, the variable is however many voxels by 180 times. Now this is going to be sort of a long call, bear with me. Normalized, bold, equals, and then in parentheses, bold reshaped, right? Take the original values, subtract bold reshaped, dot mean. And this time, instead of doing it, just letting it be whatever it was, because the time vector before, the time course before was 1-dimensional. This is now a 2-dimensional thing. We do have to specify an axis. It was a D. Thank you for the catch. And I know that the first argument it expects is the axis, so I'm just going to type in 1 from the end. And you can actually do keep, like I was mentioning before, keep dims equals true to help with some of the math.
What does keep dims mean?
It keeps a singleton dimension. So when you take the average over something, you can drop the dimension that it's holding. So if we did remember when we did this up here, I'm going to put this as false real quick. Check the shape. 25 dots. There's no 1 there. It's not actually a matrix. It's just a vector. Keep dims equals true. True. There's a 1 there. You're keeping it as a matrix with the representation that it has that column vector. Okay, hopefully my parentheses are okay. I'm looking at it right now. Cool, cool, okay. Divided by, doing some tabbing so that we can see this all in 2 lines. Bold reshaped, SD, -1 axis, keep dims equals true. It's gonna probably yell at us because it's like, oh wow, why are you doing this? But, oh, my bad. If you did that and you got that error, it says invalid syntax. That's because I'm trying to do this across 2 lines. And I forgot to wrap the entire call in a set of parentheses. Going to yell at us because they're trying to divide by zeros. There are zeros floating out there trying to be divided by zeros. So you can ignore that. That is expected. And so we can take a look at normalized bold. That shape. Okay, great. We're still have the same shape. We should have the same time vector points for every single one of our voxels. But let's actually put it back into our 3D representation. And we can do that by doing bold, normalized bold, reshape again. And thankfully, I didn't overwrite my original bold, but we can specify what shape do we want? The original bold shape. Once again, checking my spelling, run. Okay, things are okay. Bold dot shape. Hey, we're back in our original 4D shape, 4D configuration. I'm going to pause because that was a lot of typing and a lot of talking. Questions? If it looks like I did this quickly, it's because I did it last night. It took me a while to figure out which dimensions to minus what dimension. So like, don't expect it to do it in like one go. If you have this particular error right here, is it the same one? It's because there's some time points that are all zeros and it's dividing by 0. And so there are yeah, it's more like a warning rather than an error. Yes.
Is there this where all variables are
So besides the fact that yes, they do exist and they do get overwritten if I reassign them to be the same variables. I am hand waving over namespaces right now, but just sort of if you're familiar with R and MATLAB, you know how there's always like a workspace thing. There is one. It's just it's underneath. I don't want to show it. Really messy.
So I have a question.
Yes.
I'm not getting an error, but I'm not getting the dimensions out. I'm getting something function ND array dot reshape.
Function dot ND array. Ah.
Yeah.
Sorry, I'm using the same words back and forth.
So could you explain a little bit, so the first and second line, what's the difference between?
This line and this line?
Yes.
Okay. So this particular line, these two lines, which I've wrapped in an overall larger parentheses, just to make sure. I could have kept this all in one line and I will show you, but teaching wise, this is very bad. I don't want to scroll to the right. So that's why I did it in two lines, just to make sure this is just a multi-line statement. This is actually doing the normalization, right? The actual math to take the original value subtracted by the mean value of that voxel divided by its standard deviation. This performs the actual math portion, but this line right here takes that variable that has the math computed on it and changes the shape or the dimensionality of it such that it goes from a 2D array back to a 4D array. So this might help if I did it right here. Print, oh gosh, normalize bold dot shape here. Compare the shape before and after. Right, we have all the voxels that were flattened into this very large number of voxels, and then we have it reshaped back into its original real world, I guess, configuration. Of course. And just to prove a point, plot.plots normalized bold. I want to refer back to that original time series, wherever that voxel was. Copy. Paste. Yay, the same one. Just to show the same math. I did it by pulling out that particular voxel. You can also do it, in the whole entire matrix configuration. It's just a visual sanity check. All right, last but not least, I want to talk a little bit about a different package. So this is all NumPy based mathematical operations, but you would sort of assume that like a normalization function or a z-score function sort of exists. It does, it's just not in this NumPy package. There's other packages out there. There's packages called SciPy, there's packages called sklearn and skimage. There's like a bunch of these ones that all sort of sound very suspiciously similar that are very much like, okay, take the NumPy stuff that NumPy can do, put them into algorithms. I'm just going to show a really quick version of what I mean. So import SciPy, this is another package. There is a subroutine or sub package of it called signal. Sig G comes before N as SPS, just for shorthand. And SciPy is part of the installation here, so it should just load automatically. And I'm going to actually downsample my time points here. So I'm going to make a really quick time vector. We can use NumPy, NP array, n time points. And I'm just going to show really quickly what that does. It basically gives me an array from 0 to the number of time points I specified, end exclusive because it was 180, so it's 179 is the end. This is because I know the data set, the dummy data set we're working with. The sampling in terms of real world time was actually in units of 2 seconds. So at the first index, we sampled at 0 seconds. At the second index, we actually sampled at 2 seconds into the experiment. Any other issues? Okay. And because I mentioned that we sampled this at 2 seconds, I'm just going to multiply this entire array by 2. So now instead of 0, 1, 2, 3, 4, however many, it's now 0, 2, 4. NP arrange does do steps, I believe, as one of the second or third arguments, but I sort of learned how to do the math this way, so I'm going to do it this way.
Why is that useful in real life scenario?
What do you mean?
This application.
If you want to make time vectors like this pretty quickly with different scaled values. It's just in terms of, if you do like EEG sampling, you have a Hertz rate that you sample it at, you have a TR, time for functional data, basically any sort of way to make a time vector to refer to the actual coordinates you have your, let's say in this case, bold data sampled in real world time. Going back to that too, don't forget to change that back. We can now make a downsampled bold and use SPS. So from the SciPy signal, resample, take our normalized bold that we just have, that entire 40 matrix, downsample it by n time points divided by 2. Along which axis? The one from the end, because we want to downsample it in terms of time. And that last axis was the time dimension. Once again, scrolling this up, giving you guys a moment to type. I'm also going to really quickly print out the shape for you as well. Once it's done. So, right, X, Y, Z, all the same. Only thing that happened is that now we've downsampled it from 180 to 90 actual values. And correspondingly, because I'm going to do some really quick math and check me if I'm wrong, because it's really early, downsampled T would be NP array number of time points divided by 2 times 4. Yeah, 2, 4. So now instead of sampling, that's the now because we have 90 points instead of having every 2 seconds, it's every 4 seconds. Now that we downsampled it such that it's half its original length.
Why is the dividing?
The double divide?
Yeah.
It's an integer divide. Sorry, I should have mentioned that. Basically, the n time points could have been an odd number instead of 180. If we divide it by 2, it'd be something 0.5, right? We can't actually sample something to be 0.5 in length. And so dividing it, divide by 2 forces it to be floored, forces it to be an integer output. Yeah, it does rounding in the behind the hood.
It actually always,
Yeah, it's a floor computation, right?
it always runs down. This comes from, so Python is based on C. Originally, C division. And it's for reasons. It's useful sometimes.
Like in our case, 180 is nicely divisible by 2, but if it was not, then it would force it to be an integer. And just to show basically what this does, let's plot. Oh gosh, and pick a time point again. This guy. Plots. We've actually only been plotting one particular dimension, but I'm going to plot time as the X. Our normalized bold, that particular voxel I keep picking, just because it's nice. Just to show you that it's still the same guy. It's still that same time course we keep on talking about. I'm also going to plot on top of it, plots, T downsampled, T, and down, down sampled, bold, same voxel. You can sort of see it's downsampled. It's a little bit less peaky, it's a little less jagged. And the reason you can sort of appreciate why I downsampled the time vector as well. I wanted to plot it at the same scale, just to show you guys it overlays on top of each other, but it's not exactly the same time series. And you can appreciate that. I'm going to leave that up here for a second. Let me know when you guys are done typing. But essentially, SciPy also has different algorithms, interpolates, optimize, minimize routines, I believe. I'm going to pull up in the documentation to show you what I mean in a second. I still see some clicking clacking. So I'm just really quickly changing tabs to the SciPy API, or basically the documentation. And you can sort of see that there's a bunch of stuff here. There's some stats in here as well, right? NumPy, again, is mostly just for the computation portion. It doesn't actually implement any sort of algorithms in it, but SciPy takes it and does a few other things with it that might just be simpler instead of reinventing the wheel. So you can call them from here. And these are like FFT, so Fourier transforms over here, interpolates, like I was mentioning, some linear algebra, so some matrix operations are buried in here as well. Just going to the signal, because that's the one we use, you can sort of see there's convolution functions buried in here, different kinds of interpolation, filtering, right? They're implementing the NumPy operations in a more complicated or more algorithmic kind of way. And these are all able to be pulled up if you just search SciPy and then documentation. So going back over here. Cool. Great. Any questions before I literally change gears and go off to pandas?
There was a question online.
Sorry, say again?
Why is it called A-range?
A range? I actually don't know.
It's because it's, so there's a function in Python range. A-range.
I think I mentioned this. Yeah, range is the base Python, and then MPA range 4 gives you that, like as an MP array. Functionally, it does the same thing. You can throw it in a loop, but object-wise, it doesn't give you the same thing because one's a range object and one is a NumPy array object. And so, right, those dot methods that I keep on using will be different for both. I didn't know it was just to like change the range. I know range existed. I didn't know it was just like a range.
Yeah, I'm not sure.
Mine scrolling back up. I missed the line where we defined downsample T.
Of course, here we are.
Thank you.
Of course. All right. If there are still questions, we can talk offline afterwards. We have a coffee break just so we can get everyone up to speed. All right. Save. Person on Zoom, may I move on?
Yes, thank you.
Of course. All right. Open up another tab in the launcher just so we can start fresh. I am going to save it this time. Just save it as untitled. That's sort of like internally, as a person who writes a lot of scripts, I have like a fight in my heart about saving things as untitled. All right, so we talked about NumPy, sort of SciPy, and just sort of expose you to that there's a bunch of these different options for you. But this is mostly in working with matrix-like data. So, right, these configurations of ND dimensional data where you can do math on them. However, that's not always the kind of data we would get, even in neuroimaging, and even in the ways that we can save our data or receive our data when we talk to other scientists or researchers. We can also get them in CSVs or TSVs and just tabular-like data. And while NumPy can do quite a bit with that, the one problem is that there's oftentimes columns in these sort of tabular-like data that has like strings, right? I don't know, your reported handedness is right, left. How do we do math on that, right? That's not exactly straightforward. So we have a package called pandas, import pandas as PD. This is also sort of just traditional in the literature to have that as a shorthand. You'll see it very often. And someone mentioned yesterday, okay, when I was explaining what kinds of data variables we have in Python, we had that variable type called dictionaries, right? We're like, oh, this looks really similar to tabular-like data. Yes, it looks very similar. And I'll sort of explain how you can transform one to the other pretty quickly. So you're going to see these variable names again, my dictionary, starting and ending with those curly braces. First key, first column. I'm going to name it A because I can, and just fill it with some stuff. Feel free to fill whatever you want. I'm just going to type out some strings. The only caveat is that you have to have the same type of value. So if you're going to make a column, all strings, they must all be strings. If you're going to make them all integers or floats, they must all be integers or floats. Second column. See. Ooh, a lot of quotes today. And then I'll just go back to. This is just to demonstrate a purpose. So even if you do or do not do this, this is not going to change anything drastically. See. Cool. I made my dictionary just to show you what it prints like. Just a dictionary in Python with its sort of different kinds of data for every single key we have here. The one thing though that I made it as I was typing is that they all have the same length, right? There's only 4 values for every single key. So there's something sort of square or rectangular shaped about it. The one really quick way to transform a dictionary that you may receive into a pandas data frame, or that tabular data I was mentioning. I'm going to call a variable my data frame. Yeah, this is pretty common as well across the literature. PD data frame, mind the capitalization, and give it my dictionary. I'm also going to print my df at the end once I've outputted that. And so now, ta-da, a very sort of nice CSV Excel looking table. The nice thing also about pandas data frame is that it prints pretty. So this looks really nice to look at as well. And you can also have some little, if you're in the web browser, I believe you have these little highlightable toggles if you mouse over these things as well. So you can sort of already see that this is very, I keep on referring to it, but it is very Excel-like, right? This is row 0, and these are the column names, and in the values themselves, there are the values correspondingly. All right. So let's have some actual data to play around with. I'm going to be yoinking some data from the web just to show you that you don't have to have the CSV or whatever file on your local computer. You can actually pull it from the web if you already have the URL provided for you. I'm going to pull from a tractography, so a diffusion data set. There is a pandas function called read_CSV. I'm going to be pretty spaced out about it. Okay, we're going to type it together. https://Yeatsman lab. This is Jason Yeatman, in case you know him. .github.io/AFQ browser. I'm also trying not to mess this up. -demo/data/subjects.csv and that quote. This is actually a much larger CSV than we probably want to use. We're just going to play around with a few columns. There's an additional argument here that says is use cols. I'm just going to pull the first 7. 1, 2, 3, 4, 5, 6, 7. There's some NAs in here, and the documentation that when you read it provides for you, basically, there's some NAs, recognize NAS as NAs when you read it in. And then index column is actually the first column. Oh, sorry, when I said use cols, I should say 2nd to 8th. And the indexing column, or basically the subject identifier column, is that first column in this particular CSV. I'm gonna leave it up here, but I'm just gonna show you that I've typed subjects wrong. Subjects. Oh yeah, okay, we're doing okay. I'm gonna leave it up here. That URL is quite long, and also that's a bit of typing as I'm explaining. So I'm gonna let you guys go at it for a little bit. Well, basically, you can sort of see that it's printing out very nice and pretty, which is great. We have this subject ID column that was that index call, where we have our subject identifiers, subject underscore insert numbers here. We also have their age, gender, handedness, and we see those NAs I was mentioning are basically non-valued cells. Other metrics that they also measured on in this particular study, IQ, their IQ matrix, I believe, was some sort of, was it math? It's supposed to be math. And IQ vocab, basically other metrics of IQ measurements while they were doing this study. And you can sort of appreciate that this is like very similar to other kinds of subject demographic data that you might also have lying around in your lab. The one nice thing is that it prints very pretty, and it tells you how many rows there are and how many columns you've extracted, and it's formatted very nice for you to read. You can also sort of see this dot, basically ellipse saying like, there's definitely a bunch of values in the middle there that I'm not printing just for brevity. You can also call just the top 6 lines, top 5 lines with subjects.head if you don't want to print out the whole thing, if it gets too big. Before I move on, did everyone grab that URL? I know it was quite long. All right, cool, thumbs ups. Sorry, I think I got it.
Before you use the data frame,
That's right. Yeah, so underneath the hood, so for here, data frame is just making an instance of a data frame pandas object with base Python, basically. Read.csv underneath the hood is reading in that CSV file as a data frame. Yeah. Yeah, it comes out as a data frame. We can actually, very good points. Refer back to our friendly neighborhood type function. Subjects, Kelly, subjects. Type, what is the type of this variable? A pandas.core.frame data frame. And do you guys remember sort of very faintly yesterday, I was like very belaboring the point. You type a string, it comes out string. Oh, that makes perfect sense. That makes very obvious sense. This is not very obvious. What the heck is a pandas core frame data frame object? You would have to read the documentation very specifically or expect this particular object to find out all its method and associated features, right? This is sort of the bonus or the curse of having open source software. People write them however they want. They will make as many object types as they want, so they will behave however the person who wrote it wishes as well. So, yes. But yeah, the type object, the type function will also show, right, obviously, user written types. And so that's sort of the best part about it. All right. And let people on the owl/Zoom inspect that for us for a little bit. Give it a moment. Okay. So we also have other very useful methods associated with data frames that you might want to sort of play around with. Subjects.info. I am going to scroll down, sorry. I will scroll back up later if you need me, people on Zoom. We can very quickly inspect the information about this data frame object by its column, which is how it's preferably printed. This is very similar to, I believe, summary of a data frame in R, if you read that in that way, where, right, age is an integer, D type has 77 non-null values, gender has a few more non-nulls, it's an object actually, which is sort of a reference to, in fact, its character, and so on and so forth, right? You can also count really quickly which are NAS and what are not NAS with this information. Info call. We also have subjects.describe. Describe is my mortal enemy in terms of spelling, which also returns to you another pandas data frame. This time, it does really quick math on all of the numerical columns that it can do return some math on for you, such as age, count, however many non-null values, the average of those in that entire column, standard deviation, mean, quartiles, as well as minimax. Well, yeah, minimax as well. So very quickly taking a look at your data. So now we've been referencing NumPy objects with the square bracket notation, right? Oh, first 0th index, 15th column, so on and so forth. Let's try that with the pandas object. So let's say, I don't know, pull the 0th index of something from this pandas object. What's going to happen? Actually an error. It's not actually able to be referenced this way because pandas, Lord knows why, really want you to index it in the particular way that it's just developed for you. So this is, you can do it. I believe you have to do a bunch of braces, and I actually don't know the notation specifically, but I'm going to write that this is an error. And that's because if I wanted to pull, let's say the first row, I'm going to scroll back up. The first row right here is subject_00. That's actually its index. That's how it's named index into this data frame. I want to pull that row. I need to type the variable subjects subjects.loc for location, and then subject_000. And this is name base index. I should say row base, row index. Oh. And that's how we return the values from that first row based on its name. So loc for location. At least I think that's what it's called short for. Also, please appreciate that this is not another array. This is also not a pandas data frame. It's actually what is known as, hold on, I'm just going to type it really quick and then I'll remove it afterwards. Actually, a panda.core.series.series. It's a panda, it's the object called a series. So you can still sort of reference to it the same way that you would with like your regular numerical based indexing, but it also has a few funny features that you might also appreciate a little later on as well, such as having those named values. I'm going to remove that. So, right, you also have, right, the value for subject 000 age is 20. You can also grab it out by referring to it in a named way as well. I'll show that in a little bit. All right, so if you don't know the name of an index, or your index don't actually, or your rows don't actually have an index name, that's also sometimes common depending on the data set you read off the internet, you can still refer to things with subjects.iloc, and then the first row. Same. This is the numerical index base row. You can, if you also sort of think back to our NumPy, I'm not specifying row with a colon, right? Not first row every column. This is just shorthand. You can still technically call it with a colon and it's the same value out. This is just really quickly. Most people sort of think that you will pull out the entire column. Yes, we're back here again. Okay, cool. Thank you, Noah. Although you still can, if you want to, first row, second column to the fourth column. You can also still do that as well, if you wanted to. You can still subset the columns depending on the length of it is. All right, so this is a row-based grab in case you have a either named way or if you want to do it by your index method. We also can grab columns, so subjects, and then just flat out square braces, name of the column. There we go. And again, it comes out as a Panda series. It's still not a vector. You do have it with the reason why it's beneficial is because you get all the values, but you also get the corresponding indices, like the named indices of that row, in case you need them for something else later on. You can also extract the values too. I believe there's a dot values, either value or values. Let's actually take a look. Values. Values. Here you go. You can also extract out the values of that series with dot values. And this actually returns to you, if you're now very familiar with this printed notation, a NumPy array. So pick your choice. You want to keep it a series, you want to keep it, pull it out of NumPy. It is all possible. And because they're dependent on each other, they can go back and forth and they play well with each other as well. I'm going to pull it back though. I will do this dot value for NumPy array just to see the difference there. Okay, so subjects, column, age, specifically, let's pull out that subject 00 again, subject 000. And all I did was basically add another square bracket, and there it is. There's that 20 that I keep on referring to for that first subject age column.
Can you just select the column based on like the dollar?
Sorry, such a column based on,
Without like.
oh, with a number. Don't think that, can you? I don't think so, right? It's most, columns have to be named in pandas data frames for that to work. I appreciate why you want to do it that way though, as names, right? But then there's like, you know, 2 indices, zeros, and it's like, it's too much.
Yeah.
I appreciate why though, especially if you like get data from someone else and you're like, they didn't name their headers and you're like, good Lord, why? This data particularly came off that way where the first row was the indexing column, like the unique identifier, but I would assume that, you know, depending on how data is outputted by softwares, it could be whatever column. It just, there does need to be an indexing column, whether that is the column with values or the actual row number itself. So there needs to be a way for pandas to uniquely identify each element or every single observation it sees in its table. Yes.
Can you manipulate that such that like you move before?
Yes. Yes. If anyone's familiar with tidyverse, you can do pretty much everything you can in tidyverse in pandas as well. But yeah, if you want to manipulate, add new columns, take away columns, do math, subset, all those things, yes, you can. All right, so what if we want to pull 2 columns? Well, we need to provide it with a list of names, square braces, age, colon, IQ. Right. And now it comes back instead of a series, it comes back as a data frame. Right, you can again do many things. You can start to think about subsetting your data once you have it in here, pulling out specific subjects or rows, whichever you want. And just to appreciate the point, one last time, you can also combine the two. I'm actually going to start a new cell because that will be a lot. Subjects dot loc. That actually localized by, let's say, subject 0_005 to subject _0110 colon, right? Spanning, it has to be contiguous. It has to be actually a series that ranges from, in our case, rows 6 through 10, 11. You guys know what I mean? But basically, and then you can specify the column by name as well. And let's do age and gender this time, just because we can. So now we have a much babier, smaller subset, right? You can subset by rows, you can subset by columns, do it by names, do it by number-based indexing, however one of these ways that you want to do it, essentially, it is possible. The syntax is a little funky to get used to, but this is sort of the main big ways. getting yourself familiar. And this is sort of what I meant by like, you want a subset specific kind of objects, they want you to do it very specifically depending on who wrote the package. All right. Like with NumPy, Pandas provides a few basic simple arithmetic mathematical operations that you can do that you probably will do on the daily kind of thing. Let's go back to our favorite mathematical operation because it's simple. Let's do a normalized subject age kind of thing. All right, so subjects. Oop, come on, cursor. Subject means equals subjects dot mean. Oh, look at all these very familiar methods. This is a particularity about pandas. I don't know if this particular version we have on the server captures it or not, so I'm including this right here, but I'm putting in the argument numeric underscore only. So only take the means of the columns that are numeric types, just so we don't take an average of handedness, which makes no sense. And print it out for you guys. Subjects means. There we go. So, right, this is the average of the age column, the IQ column, so on and so forth. Only the numeric ones, you'd see that we dropped out the gender and the handedness column. Let's do, again, like I mentioned, our favorite mathematical operation and add it as a column to our pandas data frame. So subjects, new column, let's give it a name, age, normalized. Wow. Equals, in parentheses, subjects, age column, subtracted by subjects, age. Okay, I could refer back to the subject means age one, but I'm also going to show you a different way to calculate average over one particular column. Subjects.age, referring to that same column again, grab the mean, very similar to NumPy, divided by subjects, age. Let's see. Run that. Print it out for you, and you sort of notice that we have a new column at the way ends. That's where they get defaultedly appended. That is age normalized. So really quick mathematical operations column wise. Every single element in that column for you, if you wish to. Other very common things that we see besides normalizing stuff like z-scoring stuff or manipulating rescaling columns of numeric vectors is we can also binarize some of these columns, which I'm assuming might occur for whatever reason. So if someone's right-handed versus left-handed, you want to make it into a binary kind of thing, or you have a much larger category list and you want to put particular ones in particular groups. I'm not going to be that complicated. I'm just going to make a really simple column called subjects. Age less than 10 equals subjects whose ages are age is less than 10. This makes a new column when I print out subjects at the very end. That is a Boolean column where we have falses where people's ages are not less than 10 and they are true when they are less than 10. Slightly arbitrary what I'm describing, what I'm making here as another column, but just to appreciate this as an exercise. So, right, making new columns, you can sort of do whatever you want with these new columns. So you could fill them with values also, just sort of like long, hopefully same length vectors that is with the rest of your data frame, and you can populate it with whatever else you want. All right, so why am I doing this? Well, that is because we're currently working with a data frame that only has one index, right, subject. We can actually sort of assign multiple indices, to a data frame. And to do that, let's make a new variable. Multi-index equals subjects dot set index. And what do I want to actually be the index? Let's, instead of making it subject, let's change it up so that we use gender because there's only two choices in there besides the noun, as well as age less than 10 because there's also only two choices there. So list gender age less than 10. Close that list, close that parentheses. And I'm going to print it out for you guys. I'm going to scroll down. So, and then when it prints, still looks like a data frame, but also take a look at the left-hand side. The subject identifiers are gone now, right? Instead, we have these sort of very fun, if you are also in a browser that's nice like mine, that sort of are grouped, I would say. So this is not the world's nicest printing, I will admit. But you can sort of see what it's trying to do, even though it's printing sort of funky, is that it's trying to group together males and at false. males and then true, females and then false, females and true, right? These two combinations of indices that could, plus all these combinations that could possibly come together. So be warned, if you accidentally do this on a numerical, I've done it before. I've accidentally made my life a nightmare. But basically, there's also that NA flag as well. So remember, our gender column also has NAs in it. That also gets grouped up as a set as well. So there's a NA and then a false, a NA and a true, if those exist in this data.
I have a question.
Okay.
When we defined the variable age less than 10, are we filtering for subjects whose age is less than 10 or just asking for an argument true or false?
I'm just asking for the Boolean output, true or false. So it takes a
Okay.
look at everybody's age in that data frame, true or false, less than 10.
Okay, thank you.
Can we go further up? I think I missed that one.
Yeah, no worries. Tell me when to stop.
That one, okay.
I'll give you guys a second while I look over my notes.
Kelly just-
Okay. Can I do one more example and then I'll let you guys break for coffee because I started late? It's like, okay. Cool, all right. So why do we want to do this? Well, now you can reference it with multiple indices. So let's actually go multi-index, that's our new multi-index, that's our new kind of data frame. Back to our loc method, we can localize male and true. Ignore that. I have not been able to get rid of it. I believe there is some sort of weird pandas versioning problem, but that's not an error. It's just some warning. But basically, if you take a look at this data frame now, it's actually subsetting on all the gender, all people who reported their gender as male, and that we've calculated to be age less than 10. So now it's a subset. So you don't have to do it, you know, with crazy conditionals if you don't want to. And you can also sort of appreciate now that it's a smaller data frame, you can sort of appreciate that it's trying to group the male category here and these trues all together, like in a sorted kind of manner as well. These are corresponding rows. And the last bit is basically, right, now that you're able to subset based on these two indices. Sorry, that comment came out of a habit. Look, male, male, true, true. You can also do those same mathematical operations that I sort of showed you earlier. So numeric only equals true. Right. Is that now we're only taking the mean of these particular columns on this subset of data. And you can compare it to, let's say, instead of localizing by male true, you can do male false, female true, female false. Also the NAS as well, that really matters to you. I am going to stop here though. There is more, but I will pick that up at the beginning part of the visualization lecture tomorrow. All right, with that, if there are any more questions, I'm happy to call that a break.